Well, good morning, folks. Greetings. Welcome to Engineering 260. I hope you had a nice holiday break, a nice and safe holiday break, and we're able to, in one way or another, get together with friends or family, either remotely or at a safe distance. I myself ended up going out to walk in kind of the beach area outdoors with my mom, who I haven't seen in months, so it was really nice. Okay, we're going to cover AC power today, starting AC power this week. There is a new homework assignment posted on WebAssign. You'll see that it's homework 12 on AC power. And we'll go through what's going to be covered on that in that lesson today. The notes are posted on Canvas. There are blank slides and inked slides. And let's just go ahead and jump on in. So let's see here. Get my slides together here. Okay. So AC power has, there are tons of applications around the generation of and transmission of AC power. As you're probably well aware, the way that power is transmitted across long distances is through AC, or alternating current. And the large reason is that you can step up using transformers, which we may be able to talk about next week briefly. You can step up the current to really high, you can step up the voltage to really high values and using transformers. So you've seen transformers, things like this, like power generation stations. I'm not seeing any major transformers right here in this area, but what they allow you to do, one of the things they allow you to do is increase the voltage by a factor of 10 by decreasing the current by a factor of 10, let's say, which ends up ideally having the same amount of power transfer, right? The same amount of power. Increase the voltage by 10, decrease the current by 10, and you have the same amount of power, right? They're just scaled by a factor. However, those really long cable lines that are connecting places of power generation, like wind energy and coal power plants and solar farms and hydroelectric energy and all kinds of things. Those energy generation places are located across the continent and the world. Certainly within one continent, they're located in very distant places from us, and that power has to be transmitted over wire to us. And we know very well that all wires, even if they're made of really great materials, they still have some non-zero resistivity. In other words, they're not perfect conductors. And so you lose a little bit of energy as you transmit power over those vast distances. And those power losses are generally called I squared R losses. We look at it in terms of P is equal to I squared R, and the distance between those power lines is pretty large, so the resistance ends up being big. But if you just drop the current way down, you lose very little power. Right. So if you up the voltage to, let's say, I don't know, a factor of 1,000 or 10,000, that's why you might see some of these lines right here might be something like 12 kilovolt lines, 12 kV. I think, let's see, is that nearby? The power lines outside of your house or on the street, are those the 12 kV lines? I forget. They go higher than 12 kV for sure. But anyways, the voltages are way high and the currents are really low. So you minimize power loss. And all that is done, it turns out you can't, to get back to my point of why power is transmitted as AC, turns out you can't, because of the way induction works and things like that, you can't put DC through a transformer. It doesn't, there's no changing magnetic field, and it doesn't induce any energy in the next coil. So power is generated and largely generated through AC means, right? By like turning something around and around, a coil around a magnet. That's a generator. And that ends up being an AC kind of thing. So power is both generated and transmitted as AC, alternating current. And then it behooves us to go in and use what we've now discussed about phasors, current and voltage phasors, impedance, the impedance of inductive and capacitive elements. And we can start to look at how power is transferred in circuits that have both resistive and real impedance components and reactive impedance components. So to kind of categorize what we're going to cover in the lesson, at the end of this lesson through this week, you should be able to calculate. We're going to talk about what instantaneous and average power are. You should be able to calculate those things. We'll also introduce these terms: apparent, real, reactive, and complex power. Apparent and real are two different things. And you should be able to calculate, you'll be able to calculate those things. We're going to introduce something called the power factor and how to calculate it for a given load. And then we'll look at common inductive and capacitive loads. Utilize a technique that's used in energy efficiency to be able to transfer more real power, that is useful power, as you'll see shortly, to a load by adjusting the load's power factor to match with the circuit. It's similar to the idea of transferring maximum power that we've seen before, where you just match the load resistance with the Thevenin resistance. We're going to see ways in transferring maximum power by, in fact, matching the load impedance with in some way to the Thevenin impedance, but also in terms of the reactance of both the load and essentially the circuit driving it, the Thevenin reactance. It turns out we can adjust the power factor, and essentially by better aligning the current and voltage waveforms, as we'll see shortly, as we'll discuss in a moment. The more those are in phase, right? If you have two waveforms that are out of phase, there's a lot of cancellation there, as we'll see in the next couple of slides and throughout this lesson. The closer that the current and voltage are in phase to a load, or the voltage across and current through a load, the more that those are in phase, the more power is transferred to that load, and that's called correcting the power factor. Okay, we'll start off the lesson by going through instantaneous and average power, and we'll talk about maximum average power transfer. I actually might have rearranged these a little bit. We might actually move this effective power transfer down to here a little bit. But we'll talk about apparent power and power factor and complex power and power factor correction. Okay, so let's talk about AC power and passive elements. So you recall that for a resistor, we can assume the voltage across a resistor, VR of T, is some sinusoid, Vmax times the cosine of omega T. And if we look at the instantaneous power on that resistor, we know that the power on any element is always equal to the current through it times the voltage across it. Okay, but you can also write that in terms of the square of the voltage across it divided by, in this case for a resistor, divided by its resistance. And so if we then plug in, remember that's another flavor of the power law, power relationship is v squared over r, right? Okay, so we can then plug in this, this v max into here, this sinusoid into the voltage. So we get v max squared divided by r times the square of times the cosine squared of omega t. All right. What we'll do is we'll actually remind ourselves of a couple of useful trig functions, trig identities rather, that we'll be using several trig identities in this lesson just to simplify some of the analysis. But you'll recall that the square of a cosine of an angle, there's a trig identity that says that that's equal to 1 plus cosine of the double angle 2x divided by 2. All right, so and then let's just throw in the one for sine as well. We'll be using some of these as we go through the lesson. This is equal to 1 minus the cosine of the double angle 2x all over 2. Okay, so a couple of trig identities we'll find useful. So if we use that top identity, we can rewrite this power function, the instantaneous power, as v max over 2r times the cosine, times 1 plus the cosine of 2 omega t, twice the frequency. So we note that the instantaneous power delivered to a resistor has some DC component. It has some constant component. Because this is multiplied by 1, right? There's always an ever-present amount of Vmax, the square of Vmax over 2r, and that's always there, right? So there's an ever-present power being absorbed by the resistor. Now then if you take this Vmax squared over 2r term and multiply it by the cosine term, that's an oscillating amount. And in fact, it's oscillating at twice the frequency of the signal of the voltage across the resistor. Okay, and it cycles up and then back down again and back to 0 at an amplitude of Vmax squared over 2r. Okay, so we'll note that there is a DC or a ever-present part that just times this factor of 1 here, and then there's also an oscillating component. Okay, now if the oscillating component, there's some positive power, right? Then there's some negative power, and there's some positive power, and there's some negative power, because that's what a cosine signal does, right? It goes above and below 0 over and over again at whatever the frequency is. So it behooves us to think about, in any of these elements, and we'll start with the resistor, the average power delivered to an element. Okay, so the average power, P_av, which we'll define as P, is for any signal. The average of any signal is the average of the integral over one period of the signal. So if we integrate from 0 up to capital T, we integrate across over one interval or one period of the signal, and then divide by T. That's the average of that signal. That works for any function, right? So it does for the power function. Now, if we integrate, if we integrate something that looks like this, so if here's the DC component, right? Here's the DC component, that would be Vmax squared over R. And then there's also I should actually show this as having an amplitude of the same thing. I did not do that well. Okay, hang on. Doesn't work as well when my pen goes so slow. I can't see where it's going. But anyway, those are supposed to be equal amounts there. I guess I should have drawn that a little bit. Let's see, this should be a cosine, shouldn't it? So then this should look something like this. Okay, where this is also an amount of Vmax squared over, that's supposed to be 2R down here. Okay, so here's the DC component, right? And then this is the AC component, right? That's the time, that's the component that's changing over time. Now, if you have a little bit of power and a little less power and a little more power and a little less power, right? That signal is really, when you add it together, it's doing this, right? It's spending some time above zero and it's spending some time below zero. And when you integrate an average over that whole thing, as you're well aware, you know, you add up all the area above and below the axis, this is all equal to zero, right? So so the oscillating portion of the power, and you integrate over one period, has no effect on the average power. So P for a resistor is just the DC component, Vmax squared over 2R. Okay. Okay. Then let's talk about an inductor. So let's say we've got an inductor, we've got the current through the inductor. It's a function of time, is some sinusoid, Imax, is a cosine of omega t. And if we talk about the instantaneous power, all right, so the instantaneous power in an inductor is going to be the current through the inductor times the voltage across the inductor. Okay, and we recall that VL is equal to DIL dt, right? It's equal to the derivative of, oh, sorry, it's LDI di dt, right? And so that is equal to, if we plug in the value here, if we integrate and plug in the value of the sinusoid, it's minus omega L times Imax times the sine of omega t. Okay, now plugging that value in for VL and plugging in IL as the sinusoid here, we're getting a negative Im squared times omega times L times the sine of omega t times the cosine of omega t. Okay, that's just plugging in for IL and VL. We get an omega L, we get a negative omega L here in the front. We get an Imax squared because of the two Imax multiplied by one another, and we get the sine omega t term from VL, and we get the cosine omega t term from IL. Okay, so then if we use that another trig identity of sine omega t times the cosine of omega t, we can actually replace that with 1/2 of sine of twice the angle, or in other words, twice the frequency. So this ends up being minus omega L times Imax squared over 2 times the sine of twice the frequency, 2 omega t. Okay, if you were to integrate this function, right, if you wanted to look at what the average power consumed or absorbed by an inductor, well, what's the integral of a sine function, right, over one period, right? If you're to look at that, right, it's just, there it is, and here's all the positive area, and here's all the negative area. So it doesn't matter what the amplitude is, it doesn't matter that the frequency is twice the frequency, it's still just a sine function. And so the average power is 0. It absorbs no power on average over time. The instantaneous power at any point in time is always equal to the current through it times the voltage across it at that time. So the instantaneous power can have non-zero values, but the average power over, you know, a period over a general amount of time is 0. Lastly, let's look at the capacitor. So we'll assume a voltage across the capacitor, a sinusoid, and we'll look at the instantaneous power. We'll say that this is like any element, it's the current through it times the voltage across it. And we recall that the current through a capacitor is equal to C times the derivative of the voltage across the capacitor. And if we plug that in if we evaluate dv dt, we get a minus omega c times Vmax times the sine of omega t. All right, so if we plug that in here, we get that this is, you know, we would again get this is minus omega c times Imax squared times a, times a Vmax squared times cosine omega t sine omega t. And if you do use that same trig identity we used last slide, this is minus omega c Vmax squared over 2 times the sine of omega t, of 2 omega t, sorry. So again, it's the power is, again, it's oscillating at twice the frequency, okay? And again, we have that it's still just a sinusoid, so the average power is equal to 0. Okay. All right. So let's then take a graphical look at voltage, current, and instantaneous power waveforms. So let's say you have some sinusoidal source, right? And not all sources are sinusoidal, but in terms of power generation, and that's typically what things are, that's how power is transmitted, is as a sinusoidal function, or at least as close to a sinusoidal function as one can get. If you actually measure the power out of your coming out of your wall, don't do this with, you know, if you don't plug an oscilloscope directly into your wall, you'll blow it up. You'll blow up the input stage and possibly cause some other damage. But if you use the correct, you know, adapters and either the right oscilloscope probes, or you connect it through a suitable transformer, and you isolate the scope from the, you know, directly from the wall voltage, which is up at 120 volts, you'll see that it's actually not entirely sinusoidal. It's close, and our local power providers do the best they can to try to keep it sinusoidal, but it in fact has all kinds of sorts of noises on there. And in fact, if you are nearby inductive loads, like power tools, or you know, other motors, essentially, like if you have a large, if you have some kind of aquatic system nearby, either a pond or a fish tank, or, you know, motors in the cooling systems in your refrigerator and things like that, for pumps and all that kind of stuff. Those things are highly inductive, and they in fact can interact with the power grid in your house and create kind of inductive, you know, let's just call it noise, for lack of a better term. And those can couple into the power supply and everything that you're powering. I have a toaster oven, for example. I think it's made by Breville or something, but anyways, it works great. It heats my food really well. I love it, but the power supply design is actually not that great, and meaning that, I mean, it powers itself just fine, but some of the ways in which it's designed, it interacts with the power grid, the local power grid, in other words, the rest of the power in my house, in a pretty bad way, where you can actually see light, the entire power supply flickers at a certain rate. So all the lights in my house, if you look closely, it's not super noticeable, but if you look closely, the lights, you know, on the ceiling, the lights, if I open the refrigerator door, if I turn on any lamp in the house, in fact, any source of power, it's actually flickering at the rate that this system is modulating its own power supply. It's using a switch mode power supply, which operates at some kind of frequency. And anyway, you see that showing up in the power in the rest of the house. So all to say, it's a bit of a, you know, a bit of an aside, but, you know, the intention is that power is supplied as a sinusoidal source, and most of the time it's pretty close to, you know, we get pretty close to that, but it's not exactly that. All right, so I digress. The sinusoidal source is driving some passive linear network. And then we're going to look at both the voltage across that network, the voltage delivered to it, and the current delivered to the network. And we're also going to look at the power. So we've got voltages in red. Okay, so this is this should say V max and V max. This should also say V of t. So the voltage is in red. Maybe I should have done that in red. That probably would look better. Right, so this is V max, and then this is V of t. Okay, so the voltage is the red waveform. The current is the green waveform, and you can see that they both have the same frequency. They both have the same period, right? And then the power is in blue, and you'll notice that the power has half the period, right? 1 over t, or in other words, twice the frequency, which is what we were seeing. Now, whoops, I'd like to draw your attention to the fact that if we look here, when either of, remember that P instantaneous is equal to I, right? So if you were to write this as a function, this would be P of t, which we can try to color code it, I suppose. P of t is always equal to V of t. Well, I guess we'll do it as IV, right? So this would be I of t times V of t. And if either of I of t is 0, that makes the power equal to 0. So anytime there's a 0 crossing on the current waveform, the power is going to be 0 at that point, right? Makes perfect sense. Anytime the voltage is 0, it doesn't matter what the current is. If the voltage is 0 at any point, the power is going to be 0 at that point as well. Okay, so so in a sense, I guess what we'll point out here is that the instantaneous power is 0 when either I or V are 0. Okay, that's kind of one thing to just keep in mind there. Okay, let's talk a little bit more about instantaneous power. This is just a definition, but it is the power in watts that is provided to the network or load at that instant in time. Okay, continuing on into definitions, the average power, as we've just seen, I suppose we've already sort of derived or showed this, but the average power, which we will refer to as P, is, as we've said, it's 1 over t times the integral of the signal P of t dt. Now, the average power can be graphically shown as the bias line or the DC offset of the power signal. For any signals, as we'll see, P average, as we'll see shortly, we'll actually go through the derivation for this, is equal to 1/2 times V max times I max times the cosine of the angle in between the current and voltage waveform. So if the voltage has some phase offset theta V and the current waveform has some phase offset theta I, then the cosine of the difference between those two angles times 1/2 V max times I max gives you the average power at any time. And we'll derive that on our next slide here. So there's going to be a lot of different definitions, and we're going to go through a lot of derivations in the upcoming slides. So so hang with me here as we go through this. Okay, so let's take a look about sinusoidal analysis. Again, you know, you're not always looking at purely sinusoidal signals, but in general, power generation and transmission is done with sinusoidal signals, and it simplifies our analysis as well. And if you know how to do it for a sine wave, you can do it for any function using, you know, a sum of sine waves and using Fourier analysis, which are things that you'll get into in later courses in circuits or your junior level engineering classes. Okay, but if we take, you know, a sinusoidal source and we, you know, apply some voltage sinusoid, and then there's some current sinusoid, right? So, you know, the voltage sinusoid is Vmax cosine omega t. The current waveform is Imax cosine omega t plus theta. All right, so just for simplicity's sake, let's just assume that theta v is 0, that there's no phase offset in the for the voltage waveform, and then that allows us to track just one angle, which we'll just call theta, and we'll define that as theta is the angle between. This symbol means the angle between I and V. Okay. And so now what we're going to do is take a look at the instantaneous power of this here. So let's go through and do a derivation here. So let's say that we take a look at the instantaneous power. That's equal to IV, right? Which, if we plug in the sinusoids directly, that's Imax times Vmax times the cosine of omega t times the sine of omega t. I'm sorry, times the cosine of omega t plus phi. My bad here. Times the cosine of omega t plus, I said phi, I meant to say theta. Theta is the angle between the current and voltage waveforms. Okay, so now we're going to use a trig identity to break out this signal here. Cosine omega t plus phi can actually be rewritten as the following identity. So this is going to be, we'll have our Imax Vmax cosine omega t term out in the front.
Professor?
Yes.
I thought theta for v of t was 0, and I think for I of t is theta, right?
I of t, yeah, the phase for I of t is theta, and the phase for v of t is 0. Did I miss something? Did I skip something up here? I'm sorry, did I understand your question correctly, Jose?
Yeah.
Okay, is that cleared up?
Yeah. Never mind. Yeah.
Okay, great, perfect. Okay, thanks. So we've got Imax Vmax times the cosine of omega t. That's just this portion here in the front. And now what we're going to do is write in a trig identity for this cosine omega t plus some phase angle. Now, if I told you I remembered all these trig identities off the back of my hand, I would be lying. I don't. But they're written here into my notes, and these are the times in which you use them to make some of the analysis easier. Okay. So what we can do is replace this out. This would be a cosine omega t times the cosine of the phase angle theta plus, minus sine omega t times the sine of the angle theta. Okay, so that's a trig identity there. So you can replace a cosine with a phase offset with this rather, at first glance, more complicated version, right, of products of cosines and things like that. However, we should note that cosine of the important thing, what's helpful for us here is that cosine of theta and also the sine of theta, but we're going to it'll turn out that we're going to focus on the cosine of theta. those don't depend on time. They don't vary with time. They are some, some scalar value. If you just, cosine theta is some constant angle, right? Let's say it's 45 degrees. Let's say that the voltage and the current are out of phase by 45 degrees, right? For whatever reason. The cosine of 45 degrees is just a constant number, right? It's just a scalar. So it doesn't vary with time, unlike the cosine omega t that does change with time. Okay, so so what's helpful is for us to kind of separate those parts out, the parts that do vary with time and the parts that do not. So let's pull out the cosine theta in front here, and we'll have an Imax times the cosine of theta. I'm sorry, Imax Vmax times the cosine of theta times, now we have a cosine omega t here and a cosine omega t here. So this is cosine squared omega t minus, if now we have to distribute this Imax Vmax cosine omega t into here. And so we're going to get a minus Imax Vmax sine theta times the sine of omega t times the cosine of omega t. Okay, so all we've done is just distributed that Imax cosine omega t into the brackets there, and then pulled out the cosine theta. Okay, we're almost there. So let's now write in our Imax Vmax. So here what we're going to do is use that double angle identity. So the cosine square of omega t, we can actually write that as 1/2. Right, we did this earlier, right? Cosine square of x is equal to 1 plus cosine of 2x all over 2, right? We can use that. So this is going to be 1/2 Vmax, Imax Vmax times the cosine of theta all over 2 times the cosine of the double angle, which is, or 1 plus cosine of the double angle, which is just really twice the frequency, right? Okay, so we've used that trig identity. And then we'll do it again here as well. And we're also going to combine some terms with this sine term and this cosine term, but just trust me that this works out in the trig identities. This is 1/2 or 1/2 Imax Vmax times the sine of theta times the sine of twice the angle there. Okay. So this looks like some kind of mess, right? But here, let's actually focus on what are what's really going on here. Like this term right here, that is the DC component. That's the part that doesn't change with time, right? It's the DC offset and the power. That is the average power. So P average, which we would just write as P, as we'll see shortly, that we refer to this as the real power, by the way, is just equal to the part that does not change with time. Oops. Oh, that came out some kind of weird. What did I just do there? Okay, there we go. Imax Vmax times the cosine of theta over 2. In fact, I'm just going to write it that way. This will look more similar to how we're going to write it in later slides. Times the cosine of theta. This is what we call the real power. And it, in fact, is the only power that matters. It's the only actual power delivered to a load or network. You'll see that then there are some other components that are oscillating, and this term here, 1/2 I max V max times the sine of theta, is what we refer to as Q, the Q for quadrature, which is, that's like a geometric term or trigonometric term in terms of waveforms, but it's the quadrature or reactive power of the delivered to the load, essentially delivered to this passive linear network, which is essentially the load. Okay. Now we've talked about it. We'll talk about this more as we go through the lesson, but in earlier exercises, we've seen that passive elements that store energy react to the energy elements that they're connected to. They can store that energy and then give it back. So there's a kind of continuous exchange of energy between the power source and some element that stores energy. Okay, we say that element reacts to the power source providing that energy, and there's just this exchange of energy, and it's not, it is power that is exchanged between the source and the load, but it doesn't equate to or amount to real power transferred to the load. So for example, if you wanted to actually turn a motor to get a Tesla car, going down the freeway, it's the real power that that is going to propel it down the freeway. There could be reactive power interchanging between the three-phase, motor controller circuit pulling from the 480 volt battery pack in there or whatever, and synthesizing AC signals, and then delivering that to this three-phase inductive motor and all that stuff. There could be reactive parts that the motor is reacting and exchanging energy back and forth with the motor controller circuit. However, the reactive part doesn't do anything to propel the car down the road. It's the real or average part of power. And we'll as we go through the lesson further, we'll develop some more tools to be able to look at how real and reactive power are related, and something called apparent power and effective power. We'll come to all those things shortly. Okay, so one thing to remember as well, though, is that this load, if it's in general and in some impedance, that we can express any impedance as a real or resistive, right? The real / resistive part of the load plus J times X, which is the reactance. Okay, so this is same kind of concept with power. Okay, so we're now talking about the real power provided to something, and that's synergistic with or synonymous with the resistive power, and then we'll talk about reactive power, things like that. So what I'd like to then show, oh my, it looks like I didn't update my notes in this one, but we'll then define these things real quickly. So this is just a definition of what we derived on the last slides. We call this the real power. It's also the average power, and it's equal to 1/2 V max times I max times the cosine of theta. And if you wanted just to write yourself a note here, theta in general is theta V minus theta I. It's the difference between, theta is the equals the phase angle between V and I, as we saw on the last slide there. Okay. So that's the real power, and then the units of this are watts. Okay, just as we're used to seeing. For something I'll just throw in here and we'll come back to later is cosine of theta is called the power factor. And we'll talk about this shortly. Okay, and then finally, the other thing we showed on the last slide was the reactive power that we defined on the last slide. That's the reactive power. And we give it the symbol Q. And it's 1/2 Vmax times Imax times the sine of theta. Oh, and the units of this are in VARs. Okay, and that stands for volt amp reactance. Okay, it's to not confuse it with watts, which are actual power delivered to a load, and the fact that we can try to categorize and keep track of the fact that it is units of volts times amps, which is technically the units of power, but it doesn't transfer any actual power. So we call it volt amp reactance to distinguish the two of those things. Okay, now how do you transfer maximum average power to a load? So let's say you have a linear circuit over here connected to some impedance, some load of impedance Z sub L. And we know that we could then Thevenize this circuit here as a Thevenin voltage phasor in series with a Thevenin impedance Z. And so the question is, what value of Z sub L will receive maximum average power? And I left these notes on here for just the interest of time. For this is kind of a derivation that we don't have to spend the time going through. And in some ways, it's similar to the derivation we did for maximum power transfer with Thevenin resistance, not Thevenin impedance. Okay. So now we're looking at just general power transfer for AC power. We note that Z Thevenin is some R Thevenin plus J times X Thevenin, the reactance part, the real part, and the reactive part. We note that, and I'll just kind of, just motion you through the parts of this, and you can look through this in more detail if you want. The book has a good description of this. This is all derived in the book in chapter 11. So the phasor I is then the current going through this thing here. The current through this is just V Thevenin, the phasor V Thevenin divided by Z Thevenin plus ZL, right? Okay, and so you can write that as V Thevenin over R Thevenin plus RL plus J times X Thevenin plus XL. Okay, now if we want to look at the power, that's going to be 1/2 I squared times RL. So if we take this whole thing and we plug that in for I, we get a V Thevenin squared down here. We get these terms squared down here in the denominator. And then essentially what you're going to do if you want to find out how to maximize this, simply just take the derivative with respect to one thing. We can take the derivative with respect to the reactance, XL, and you get a kind of a quadratic or a quotient rule in the derivative there. And so you kind of go through the motions. And I'm just going to kind of skip over these parts because I don't want to spend a lot of the time on the derivation itself. But essentially, you arrive at the fact that if you look at the two equations, you differentiate P with respect to the reactance, which we saw down here on this slide. Okay, and then you also differentiate P with respect to the resistance, RL. You end up with two equations. And essentially what they say is that the punchline, if you will, is that the load impedance to maximize power the load impedance should again be set to the Thevenin, the load resistance, sorry, the real part, should be identical to the Thevenin resistance. And that's the same as it was for when we were just looking at maximum power with just resistive circuits, right? And then for the reactance, it turns out, as you go through the analysis, it turns out the reactance of the load should be negative the reactance of the circuit, the Thevenin reactance. Okay, so essentially that's it. ZL for maximum power should have the same real part, the Thevenin resistance, and a negative reactance to whatever the Thevenin of the circuit was. So negative JX Thevenin. Essentially, that's the complex conjugate of Z Thevenin. So ZL for maximum power should be set to the conjugate of Z Thevenin. And that's the takeaway. How much power is actually transmitted if you in fact connect a load that does have the complex conjugate of the Thevenin impedance? It turns out that it is, without going through the whole derivation, but essentially you just plug Z Thevenin into this equation up here. P is equal to 1/2 I squared RL. You plug in Z Thevenin for this. That should say ZL, ZL. But you plug in Z Thevenin conjugate for this, and then you end up getting, but it's V Thevenin squared over 8 times R Thevenin. That's the total maximum power there. So again, I left some of the notes in there which align with the textbook. You can look through the textbook if you would like more detail. But the takeaway that all that you really need to focus on is summarized on this slide, and that is that for maximum power transfer, you want to set the load impedance equal to the complex conjugate of the Thevenin impedance Z Thevenin. So set RL to R Thevenin, set the reactance XL, the load reactance, equal to negative of the load of the Thevenin reactance. In other words, ZL should be equal to the complex conjugate of Z Thevenin. And calculating the maximum power is V Thevenin squared, the magnitude of the phasor V Thevenin squared, okay? So keep that in mind. You can't find like the DC value or something. You need the magnitude of the phasor V Thevenin squared over 8R Thevenin. And shortly we'll get to some example problems that go through this. In fact, by shortly, I mean right now. Okay, so here we've been given a circuit that has a voltage source with 60 volts at a phase angle of 120 degrees. And we don't know the frequency, that hasn't been given to us, but the impedances of the capacitive and inductive elements have already been calculated. Whatever omega is, that's been calculated. So whatever omega is and whatever the values of C and L are, those have already been calculated at that omega, and they give us negative J10 ohms for the capacitor and J20 ohms for the inductor. And so we want to find the impedance ZL connected across this port here that will receive maximum power from the circuit. And what is that maximum power? Okay, so let's go ahead and jump in. So Z Thevenin is, remember, this is the equivalent impedance after turning off the independent sources. Okay, so Z Thevenin is the impedance seen looking into this port, right? Okay, and after we turn off those independent sources, if we turn off this voltage source, that just shorts this, right? This gives a short across there by turning that off. That's how you turn off a voltage source. And so, so what do we see? We see that there's a Z Thevenin we see a 5 minus J10 in parallel with this J20 here. And then that's in series with the 2 ohm resistor right there, right? After you short this voltage source, the 5 minus J10 combo is in parallel with the J20. And then all of that whole combination is then in series with the 2 ohm. Okay, so that gives us, if you calculate this out without spending all the time, you know, working through the phasors on this, that ends up giving us an 18 minus J2, or in other words, so there's the real component and here's the reactive component of Z Thevenin. Right, so keep that in mind as you're looking at this stuff. Z Thevenin is going to be equal to R Thevenin plus J times X Thevenin. And if we find out each one of these things, we actually now know that this is, hang on here, this is R Thevenin, and this is X Thevenin. Okay, so looking at that in magnitude form, we see that this is, because we'll need that as well, 21.63 at an angle of minus 33.7 degrees in ohms. So if we then wanted to calculate Z Thevenin, I'm sorry, ZL, should equal, oh, that's not a phasor, sorry. ZL should equal the complex conjugate of Z Thevenin, which is equal to 18, not minus J2, but plus J2, right? The reactance has the opposite sign, or that would be at a magnitude of 21.63 and an angle of positive 33.7 degrees in ohms. Okay, so that's there's the impedance, ZL. We've solved for that. And then finally, we can calculate P max. Okay, so remember that P max is equal to V Thevenin squared, the magnitude of V Thevenin squared, divided by 8 times R Thevenin. So to find V Thevenin, we can use, realize that V Thevenin is equal to VOC, right? It's the open circuit voltage at that port. Okay, so if we if we acknowledge the fact that when it's open circuit, there will be 0 current flowing through that 2 ohm resistor. And if we just consider this as kind of ground right here, then this is V Thevenin, right? Okay, and so when you see it that way, it's easy to see that we can use voltage divider equation. So V Thevenin is equal to the impedance, it's across this impedance, right? It's across the J20. So over J20, or J20 over 5 minus J10 plus J20, all times the source, 60 volts at an angle of 120 degrees. And again, without going through all the phasor mathematics, we've gone through that in earlier sessions. V Thevenin is then equal to 107.3 volts at an angle of 146.56 volts. And then now that we have that, we can easily go and calculate P max. Remember, it's the magnitude of V Thevenin, and we have that magnitude there. So it's 107.3 volts squared over 8 times R Thevenin, which is this 18 ohms there, which we had calculated. And I don't have that handy. What is it? It's 107.3 squared divided by 8 times 18. We get 79.95 watts. Okay, and if we wanted to highlight the answer for Z Thevenin, that's it here. Or you could also write it in that way. Okay, let's see. We have time for another example here. One thing I will recall really briefly before we go forward is just that, oops. Should just recall this before we move forward here, is that for a resistor, the power in a resistor is, the average power is V squared over 2R, right? And what I will point out is that the power for, the average power for a capacitor is 0. And then the reactive power, QC, is going to be VC squared over 2 times the reactance of the capacitor. And for an inductor, remember that the power, the average power or real power delivered to an inductor is 0. But its reactance is V squared. It's going to be VL squared over 2 times X sub L. And this is a C, and that's an L down there. Okay, so those are some handy formulas to have in your back pocket if you need to calculate the reactive power of a capacitor or an inductor. It's 1/2 the square of the voltage over the impedance, over the reactance rather. Okay, let's take a look at one more example here. So this is the same circuit. I'll just erase this part here where we shorted it. This is the same circuit, but we're now asked to find find the resistance RL. Okay, that's different than finding the impedance ZL of the load that receives maximum power from the circuit. Now we want to find the resistance RL of the load, so a purely resistive load. Okay, so now we're not connecting a load like Z sub L like this. That's not what we're doing anymore. That could have an inductive component or a capacitive component. What we're doing at this stage is just connecting a purely resistive load RL and trying to figure out what resistive value to connect to this circuit such that it receives maximum power. Okay, so what we can start with is we know that P max, that the power is maximum rather, when RL is equal to, now this is something that I did not focus on as much in the derivation, but when RL, if there's no reactive component to the load, then RL for maximum power is equal to the square root of R Thevenin squared plus X L squared. I think that's actually supposed to say X Thevenin. My notes said XL, but that doesn't make any sense because there's no reactive component to the load. And then also, if you look at that in terms of, if you think about this in terms of, this is R Thevenin, and let's say this is X Thevenin, then the impedance Z is the Pythagorean or the geometric sum of R Thevenin and X Thevenin in the complex space. And so that's equal to the magnitude of Z Thevenin. I keep writing bar over that Z. It's not a phasor. Okay. My notes, by the way, that I posted on Canvas have a bar over the Z. That's why I keep getting tripped up. I'm actually using these notes, and some of these notes are in a version from a colleague of mine. Okay. At any rate, so Z Thevenin is equal to, we already found Z Thevenin from the previous page. It's equal to 18 minus J2, right? That's what we found. We found from the previous page that it's equal to 18 minus J2 ohms. And in magnitude phase form, that's 21.63 at an angle of minus 33.7 degrees. Okay, and that's from the previous page. We can just write ourselves a note there. Okay, now V Thevenin, actually this is also from the previous page, because we calculated what that is. V Thevenin, which is a phasor, is 107.3 at a phase angle of 146.56 degrees. So RL then should be the square root of R Thevenin plus X Thevenin squared. So this should be the square root of 18 squared plus X Thevenin is 2 squared. Did I have my notes wrong? Might have written this wrong. I did write this wrong. Okay, sorry folks. On the previous slide, the reactance in Z Thevenin was actually J12, not J2. So if Z Thevenin is 18 minus J12, not J2, then ZL should have been set to 18 plus J12. Okay. Oh, whoops. Can't write here. Okay. J12. Okay. The magnitude and phase is still already correct by my notes, but I had just not written that quite correctly. Okay. So this is J. So from the previous slide, it's Z Thevenin is 18 minus J12 ohms. And that's going to then, if we're looking at our L, it's the square root of 18 squared plus 12 squared. Which gives us, oh, you know what? We already have that. It's 21.63 ohms. We actually already had the magnitude there, didn't we? Okay, so how do we then take that and figure out what the maximum power is? Okay, well, if it's purely resistive or purely real, right? So we know that P max is equal to IRL squared times RL over 2. And that comes from, for us, that's, it should be I squared R. And so so here's what we'll do. We'll put this in here. This is, if we have, if we take a look at the Thevenized circuit, here's V Thevenin, the phasor, going through Z Thevenin, which, remember, that's equal to R Thevenin plus J times X Thevenin. And then that's connected to RL. And we're looking at the current IRL going through this load here. That's the phasor. We can actually calculate that pretty simply. That's just equal to IRL over, the current is V Thevenin over, well, it's going to be R Thevenin plus JX Thevenin. In fact, let's just group the real parts together, right? So this will be R Thevenin plus RL plus JX Thevenin. Okay, and then what you want to do is actually is find the magnitude of this thing. Okay, so if you're looking at the magnitude, then this is going to be the magnitude of the phasor IRL is V Thevenin over the square root of R Thevenin plus R Thevenin squared plus RL squared plus X Thevenin, essentially. And then once you have that, you can plug this into IRL and solve for the maximum power. Okay. What I will do then is just look at, in fact, let's just leave it off there, and we'll start our next session looking at effective power. So I believe this will let you get started. This first bit that we've gone through and a few examples will help you get started on the homework that's posted. And we'll pick up the discussion and talk about effective or RMS power, apparent power and power factor and complex power and power factor correction. We'll cover those on Thursday. And so with that, I'm going to stop sharing my screen. And those of you in the lab, I'll see you in lab this afternoon. And otherwise, I'll see you Thursday. Till then.